Hello, students. Today we want to talk about how we can use the mean value theorem to actually prove results about functions that I think you will find to be some of the most useful consequences that we have had in the course to date. For instance, we will now use the sign of the derivative to determine whether or not the function increases or decreases or is actually constant. And then with those ideas, we can actually construct what we call a first derivative test, which will be a test for relative extrema, which is putting us on the road to classifying optimal values. That is, when we talk about optimizing a function, we want to find largest values, smallest values, maybe relative values, or absolute. The nice thing about that is that we can characterize functions in a more precise way than we could before we had the objects and the definitions of the calculus. Remember, in the prerequisite courses, we could utilize many good strategies to analyze functions, but finding the actual existence of maxima and minima was something that was not often available to us unless we just had functions that were already giving it to us. For instance, like the quadratic function. We don't need calculus to optimize a quadratic function. But again, we have taken all of the strategies from the previous courses, and now applying the new techniques from the calculus will now give us the complete picture. So let's go ahead and look at some ideas that the mean value theorem will give us. Now, as I was saying, the increasing decreasing question can now be answered. We had no ability to do that. For instance, in the prerequisite courses, we could often evaluate a series of points and intuitively think that for particular intervals, the function values would be growing or the function values would be getting smaller, but there was no precise way to analyze that. Now with the derivative, we do. Of course, we do need the mean value theorem, so we will need those hypotheses. But let's just go back to our definition of increasing and decreasing from the prerequisite courses so we can basically refresh our memory. We're finding that lots of the definitions from the prerequisite courses are now being used quite heavily in the calculus. Maybe at the time you didn't see how they were that important. For instance, you got these nice definitions, but you could rarely use them. Now you see why these particular definitions were afforded at that point, so you can use them now in the calculus. So let's, for instance, assume that f is defined on an open interval I. And this can be done in many contexts, but we'll just keep the treatment to the open interval, which is a convenient way to discuss the calculus. And we will say that f is increasing on I if the values get larger. So first, what we will do is we will take two elements in I, we can call them x1 and x2. And then, of course, if x1 is less than x2, if f increases, then the value at x1 should be less than the value at x2. That is, as you move through the interval, the values of f actually get larger, okay? And so for decreasing, there's just one adjustment. Again, f decreases on I if for x1, x2 element in I, if x1 is less than x2, then the values actually get smaller. That is, the function value at x1 is greater than the function value at x2. So that is really what we had in our previous courses. And this degree of precision is needed because the algebra will tell us if we have an increasing function or a decreasing function. We just need a way to assign the arithmetic in a precise way. So how does it work? Well, let's go. This particular theorem we sometimes call increasing decreasing. I mean, it doesn't really have a name, but we could just say the increasing decreasing theorem. We like it when there's a nice buzz phrase for the theorem, like Fermat, EBT, MBT, things like that, Rawls, but this does not carry a specific mathematician. So sometimes we just say increasing, decreasing theorem. Now, as I said before, we need the hypotheses for the mean value theorem. That is, we need continuity on the closed set and differentiability on the open. Again, like I said before, this can be replaced by differentiability on the closed set, but the standard way to state these theorems is as we have done here, and we will continue to do that. So how do we characterize increasing, decreasing with the derivative? This will not be a surprise to you. That is, if the derivative is actually positive for values of x in the open interval, then the function increases on that interval. And then, of course, we can extend the increasing to the endpoints. Points don't provide us any set of content, so extending to the endpoints is simply an algebraic maneuver that would be available to us regardless of the situation. So just remember, in problems, the directions may be to supply the open intervals of increase or the open intervals of decrease. You have the luxury of being able to apply the endpoints to the open intervals if that is something that is good or useful for the problem that you are working. So removing the endpoints or adding them will not change the value nor the accuracy or precision of the theorem. Now, for the other case, we have two more cases. If the derivative is actually less than 0 or negative for x in the open interval, then we get f decreases on the closed set. We can extend to the endpoints, use them or not. And then another thing that is actually very useful to us is that if the derivative is identically 0, then the light bulb comes on and says we have neither increase nor decrease. We just have a constant function. So now we have basically reduced increasing, decreasing, and constancy to arithmetic problems. That is, just like solving an inequality in the prerequisite courses, we were interested in the boundary values to see where the function would change sign. And then with the changing sign or the sign analysis, we're able to solve inequalities with great efficiency. And so there is no reason that we will leave any of that. We will do our number lines and do our sign analysis in the same efficient way that we did in the prerequisite courses. So that is really a valuable technique that you already know how to do. We will now apply the derivative to supply the correct credentials in order to make the correct assumptions about the function. Now, let's look at one particular example here of how we actually use the mean value theorem to actually prove a result. So I've started the sketch here, and of course, all of these proofs are in your notes, and so you can look at these and then as you continue to work through the problems, applying the result, go back and read the proofs, work through them. I think you'll find them very, very straightforward. Now, let's just look at an example where the derivative is actually positive on the open set. And so just like we normally do in the definition of increasing and decreasing, we will take two elements in the open set and then assume that x1 is less than x2. Okay, now this is where we have the power of the hypotheses. Remember, the function is continuous on the closed set, and it is also differentiable on the open. So what this gives us, and I'll put this in red because this is very important, this gives us continuity of f on the closed set and differentiability on the open set. But we're just simply characterizing the hypotheses in terms of the definition of increasing. or decreasing. I mean, we haven't established anything yet, but that's what we're doing. We're looking back at the definition and applying that notation. So this is very powerful here. Because we have this, we now can invoke the mean value theorem for this particular interval. That is, the A has been replaced with x1 and the B has been replaced with x2. So this is a little microcosm of the interval. And if we can show that this happens for any pair of elements x1, x2, then we have covered the result. This is the arbitrariness of choosing these two elements in the domain. So now by the mean value theorem, we have the existence of C between x1 and x2 such that the derivative of f at C is the slope of the secant line. And of course, the secant line is just rise over run, f of x2 minus f of x1 divided by x2 minus x1. And by hypothesis, this derivative is positive, so this difference quotient here must be positive. Okay, so that is the key relation in the arithmetic that I was talking about earlier when we were discussing the mean value theorem. This is the critical piece of information that we did not have in the prerequisite courses. So now we look at this, and this is just like the Fermat's theorem. We know that x2 minus x1 is positive by hypothesis. So this implies that the numerator must be positive. That is, f of x2 minus f of x1 must be positive. Now, of course, we can just simply transpose. So we have f of x2 is greater than f of x1. So now when we look at this, we can make our deduction. That is, now what we see is that if x1 is less than x2, then the value at x1 is less than the value at x2. So the values of the function are getting bigger. That is, the value at x2 is greater than the value at x1. You can say it however you like. And so therefore, again, due to the arbitrariness of the x1 and x2, f increases on the closed set AB. So we can extend to the endpoint, so to speak. Now, if you think I've made the huge leap here, I said the arbitrariness, based upon the fact that the x1 and x2 are arbitrary. So what I can do here, not to just slip over that, let me just say this. Therefore, f increases on the closed set x1 to x2. And now, due to the fact that the x1 and x2 are arbitrary, it follows, that's maybe a better way to do it, it follows that f increases on the entire set. So one thing about mathematics is the abstraction. That is, we take two values in the domain and apply the result. This would work for any two elements, x1, x2, for any. And so due to that arbitrariness of our argument, we can now extend the concept to the entire interval. So that is the elegance of our proof technique, and also the just ingenious use of the mean value theorem. So again, as you start to work with this, use the result, then come back to this theorem and see that you have the result that you need. Again, we had to have some way to connect the arithmetic of the secant line slope with that of the derivative, and the mean value theorem gives us that. So the sign of the derivative is now connected to the slope of the secant line, which gives you the comparison between the values of f, which we did not have before, okay? Now, one thing that's interesting is that when we think about trying to analyze sign increasing, decreasing, then we're just going to look at critical numbers we're going to look at all the possible BVs. For instance, when we analyze the derivative, we will look for BVs and combine all of those into a sign test. And then we can figure out the value, that is the actual sign of the derivative. And I don't really know that we have to say specific values. We just need to know that the particular function is positive or negative, and that will give us the increasing, decreasing. So we don't have to pick points so much as we have to look for generalities, and we can use multiplicities to our advantage when trying to analyze signs. Now, what's important here is we have another result that I want to share with you. It's called the first derivative test. And it is super simple. That is, now that we have this sign convention with increasing, decreasing, that obviously will give us the existence of relative minima and relative maxima, because you think of increase, then decrease, that will define the relative maximum. And then you have decrease, increase, that will define the relative minimum. So the increasing, decreasing theorem basically gives us the first derivative test. Now, what we want to do is think of this as a local result. So let's just see what we need. And of course, we call this FDT for first derivative test. So this has a nice name. We don't forget it. And it's, again, like EVT, MVT, very useful. And we will use them to make our proofs very succinct and very efficient. So now let's just see what we need here. We need C to be a critical number of a function f that is continuous on an open interval I containing C. So again, we need the continuity of the function on the set containing C. If f is differentiable on I, okay, if we have the differentiability, which we need when we're trying to discuss increasing, decreasing, except possibly at C. We don't need the differentiability at C. We can always extend to endpoints, not a problem. Then f of C can be classified as follows. So just like I was saying before, what we want to do is look at the C and the nice symmetric interval, or not necessarily symmetric, we like symmetric, about C, and consider the sign of the derivative on either side of C. That's what's going to give us the relative extremum. So in words, if there exists a delta positive such that f prime of x is less than 0 to the left of C, as we have here to the left of C, and f prime is positive for x to the right of C, that is between C and C plus delta, then we have f of C is a relative minimum. That is, we're decreasing, then increasing. That defines the valley, so to speak. So what we're thinking of here is decrease and then increase. So we have the valley, so to speak. Now, of course, it could be a cusp or whatever, no problem. I mean, you know, I just drew it so it looks like a horizontal tangent, but we could have something like this. Could have something like that, decrease, increase. That would be the same because we're not assuming the differentiability at C, but that's not an issue. Now, of course, what about the relative maximum? Well, we'll just flip it around. So if there exists a delta positive such that f prime of x is greater than 0 to the left of C, okay, to the left, C minus delta to C, and f prime of x is less than 0 for x element of C, comma, C plus delta, that is to the right of C, then we have a relative max. So we have increase, decrease, relative max, or maybe we have something like this, relative max, relative min, relative min. So this is exactly how the increasing, decreasing automatically gives us the first derivative test. And so when you think back to your prerequisite courses, when you drew your number line and you plotted your boundary values and you check sign using multiplicities, that's a very quick, efficient procedure. And that's exactly what we're going to do with the increasing, decreasing. And then, of course, when we analyze increasing, decreasing, we automatically get the first derivative test as a freebie. So really, really nice result the mean value theorem gives us. Now, of course, and this part 3 is like, well, do we really have to say this? Well, if the sign doesn't change, then you don't have a relative extremum. So we think about our favorite example. What's our favorite example? The cubic function, right? It has the 0 derivative, the horizontal tangent, but the function increases throughout its domain. So we increase to the left of 0 and we increase to the right of 0. That is, the sign doesn't change. Okay, so we don't have a relative extremum. I mean, you think, well, why do we even need to say that? That well, there's just, you know, I guess if we didn't say it, it would be okay, but we do state it. So the beauty of this is the simplicity. So let me just show you what I was talking about here. When we think of just a quick derivative or quick proof, you can go back through this and then convince yourself that this is quite simple. That is, decreasing, now we have extension to the closed set here, decreasing, and then increasing like the pictures I just drew. So therefore, we have f of c is less than or equal to f of x for x in the open set, okay? But that, of course, defines a relative minimum. So we go back to the definition of relative minimum and we see exactly what's going on. So the increasing, decreasing gives us automatically the first derivative test. So, and you can look through the other ones to verify how simple this is. So not all proofs in calculus have to be difficult. I don't want you to think that everything requires arduous work. And this is one that we automatically just get for free with the mean value theorem. So let's just see these results at work. It's nice to have results that give us arithmetic, that give us power. So let's look at the problem that you just saw at the bottom of the page. So what we want to do is determine intervals. And here's, let me just state this. Some problems will state open or closed. Let's just say determine open intervals of increase and decrease. And then classify any extrema, classify any relative extrema. So in this particular case, we can utilize the following function. That is, we have f of x, and we have a given domain. So that'll make the analysis a little simpler. We have f of x equals x over 2 plus cosine x. So we didn't do very well with these kinds of functions in pre-cal because we just didn't have a way to associate the algebraic function with the transcendental function and get very far. We didn't have the machinery of the calculus, and we're given that x lives between 0 and 2 pi. So we've had examples like this before where we had a domain of definition. So we don't have to worry about computing this. So the first thing we want to do is say, okay, well, if we need to figure out the sign of the first derivative, first thing we would do is make sure we have the definition, of f, which we have. So now we need to compute the derivative and then analyze it. Look for boundary values, or as we call them now, critical numbers, okay? So f prime will now be, again, the derivative. We have 1/2 times x, so that just gives us 1/2. And of course, the derivative of cosine is the additive inverse of sine. Now, if you like, you can rewrite this in a way that's a little bit more user-friendly. We can factor the negative. We could say negative sine x minus 1/2, like that. Now, of course, if you factor things to make them look better, then you can't forget the negatives you factored, because that will affect the sign. So remember, if you do this, then we've got to be very vigilant when we actually compute the sign. Let me stress this, just like when you did inequalities in the prerequisite courses, if you did any factoring, then you would always have to keep that sign that you factored, especially if it's negative, obviously. You must keep that when you are determining signs. So don't be negligent of things like this. Now, of course, when we look at this, we're thinking, okay, we've got continuity on this set. We just now want to look for zeros, because that would be places where the function can change sign. And of course, we have this factor only occurring to the first power, so multiplicity is just 1. So this will be equal to 0 if and only if sine x equals 1/2. So now we can use our trigonometry. So if and only if x is equal to the inverse sine of 1/2, which is pi over 6. But of course, now we know that the sine function is not 1-to-1 in 0 to 2 pi. So we use, what is it, Professor Ron's lemma, which basically means we have another solution in the upper arc. And we'll just say second solution is pi minus pi over 6, which is now 5 pi over 6, just using the symmetry of the unit circle and the fact that the sine function is odd. So now we've got two critical numbers, or boundary values. So again, we now know that we have a limited domain, so we didn't have to extend these to all possible solutions. And that's okay if you do. You'll just have to pare it back to meet the domain that we have here. So now we can think of critical numbers or boundary values. So you want to state that maybe critical numbers. Again, that we were thinking of boundary values in our previous courses. So we have pi over 6 and we have 5 pi over 6. So now we do the same analysis we did before. We're pairing this off. We have the 0 to 2 pi, and then of course we just want to write these in numeric order and don't worry about it looking like Rembrandt. So we have pi over 6 just spread out, and then a 5 pi over 6. Of course, this occurs to the first power, multiplicity 1. Now notice this is what we have to do. We want to test the sign of f prime. Notice if we take values here, the sine function in this particular interval, when we think about it, is increasing. That is, the values are getting larger. So if we take a value here, this will actually be negative, okay? And then when we apply, in this case, the negative here, we get positive. So one thing we want to be careful about is the negative that we already have here. So don't forget that. So now we can do a little sign convention. So we've got plus here, and then of course we have the multiplicity here. We'll have to cross and then back up. It's not just the case that things work for polynomials. We can use multiplicities with other types of functions, especially trig functions, because they have similar continuity properties as polynomials. Okay, so now what we need to see here is that we have a plus increasing, we have decreasing for a negative derivative, and we have plus here. Now, the way to invoke the first derivative test is to just use arrows to indicate increase, decrease. So here we have increase, decrease. So what we have defined here is a relative max. So we say relative max, and we'll just write it f of pi over 6 right there. Now, of course, we have decrease and then increase. This defines the relative min. It is so simple, you don't have to write an expansive chart because this is trivial. It's just a sign analysis, and this gives you all the information you need. You just have to be careful of the assignment of the signs. If you've got a correct beginning, then you can move that into the entire line, again, considering the fact that you may have some even multiplicities where you would only touch the line. So keep that in context also. So here we have a relative min of f of 5 pi over 6. So basically, we've answered the question here with this number line, but we want to be a little bit more succinct. So now let's go ahead and write down the open intervals of increase. So we'll say increase, increase, again, in the context of open intervals. So we'll take 0 to pi over 6. And then the second interval will be, again, where the derivative is positive, and we'll have 5 pi over 6 to 2 pi. So in many cases, the open intervals or closed, whatever you're asked to do, you just basically be asked to separate them by commas. Okay, we're not assuming that the function is one-to-one. Okay, so we're just looking for intervals for where the function actually increases. Okay, and you just separate that with a comma. Again, these are connected, these intervals are connected, so we're just using the number line. And then for decrease, we've just got one, the open set from pi over 6 to 5 pi over 6. And of course, if you want to extend to the endpoints, you certainly may. Now, we just now, and here's another thing that you have to be aware of. Remember, the first derivative gives you increase, decrease. It also gives you relative extrema. But to find the actual value of the function, you go back to the original statement. It's sometimes very easy to make careless mistakes when you don't think about what you're doing. You get focused on the derivative, and then you forget the values are actually supplied by the original function. So now let's go ahead and write these down. We're going to need f of pi over 6, and this will give us pi over 6 divided by 2. Very simple, cosine of pi over 6. So this will give us pi over 12 plus square root of 3 over 2. Now, of course, if you're going to write this, there's no need to simplify this. This is certainly fine. It's exact. And then as we know here, the f of pi over 6 gives us a relative max. So we say relative max. Now, of course, you can always include the x value where this exists and write it as an ordered pair. But just remember, the relative max is the value of the function. And in this case, it occurs at the input value of pi over 6. And now let's look at f of 5 pi over 6. Again, this puts you right back to pre-calculus doing inequalities. Again, if you spent the time on those particular arguments and strategies as we see here, then this will be very, very accessible. Hopefully that is the case. Again, utilizing what you already know how to do. So we have 5 pi over 6. So 5 pi over 6 divided by 2 plus cosine of 5 pi over 6. Of course, the reference number or angle for 5 pi over 6 is pi over 6, but the value in the second quadrant is negative. So we get 5 pi divided by 12 minus the square root of 3 over 2. And this gives us a relative, as we see here, relative minimum. So when we think about the process here, we see that the key to all of this is the increasing decreasing theorem. The increasing decreasing theorem naturally gives us the first derivative test. It's like it's right there. And what, like I say, will help this bring a visual to you is once you actually do the sign convention. And again, this little line or little curve that I draw is just simply amplifying the fact that we have positive here, we drop below the axis. This is not trying to draw the curve in any way. It's simply notating where the curve F is relative to the x-axis, okay? And so well, in this case, the curve F prime, obviously, that relative to the x-axis, where is it positive? Where is it negative? So this F prime tells us so much about the function. That is, the sign of F prime tells us about the increasing and decreasing of the function. And so this just gives you a visual to say, okay, it's positive here, it's negative here, it's positive here. Whatever type of convention you want to use, that is fine. But I found this is a very effective way to visually illustrate the value of the particular function that you are analyzing. Okay, let's look at another example. So again, normally what you'll do with these problems is you'll correlate the two. You'll answer the increasing, decreasing, and then move that into the relative extrema. This is actually where you start enjoying the confluence of the algebra with the derivatives, which is really kind of nifty. So here we have, again, we want to do the same thing. Example, determine open intervals of increase and decrease and then classify any relative extrema. Again, you just get one with the other. So here's the function. This is a little bit different. This is algebraic completely. So we have f of x is 14x plus 1 over x. So again, there is no domain of definition for this one. And so we want to analyze this just like we did the last one. So just remember, now that you've seen me do lots of derivatives where I always manipulated the derivative to make it more accessible to analysis, I think you're seeing why that was the reason before. That is, we want to prepare or write the derivative in a way so that we can easily analyze critical numbers, that we can look for those boundary values. And again, what's important here is that even if we do not have a critical number, we're still looking for boundary values. For instance, if there's an element that's not in the domain of the original function, we're not going to find it in the derivative. So we still need to include that as a point of discontinuity, as a boundary value. So even if it doesn't fall into the category of the critical number, it is still important when we analyze the sign of the derivative. So don't fall into that trap. Use what you already know about solving inequalities. And this is a really important example where I'm alluding to what I just said. Notice here, the domain does not include 0, clearly because division by 0 is undefined. So we have negative infinity to 0, union 0 to infinity. Now what we want to do is simply analyze the derivative. Okay, now just for convenience, let's just write 14x plus x to the minus 1. Now you could get kind of creative with the factoring here, but I think we'll be okay. We'll factor it as we move through the problem. But whatever you do before you take the derivative is certainly up to you. But I think I'll leave it like this for now. So we have f prime will just be 14 minus x to the -2, just using the simple power rules. So when you look at this, you're like, okay, well, we're ready for a common denominator or a factorization. Now notice here's the value of x to the -2. So maybe what we could do in this particular case, if we factor this, and then worry about signs in a minute. So first, let's go ahead and factor the x to the -2 and see what we get. So we have x to the -2 times 14x squared minus a 1. Okay, so the idea is that we know that we're going to have x's that end up here. So we maybe don't want to factor the negative with the x to the -2. So now when we check this, we get the 14, and of course, we get the negative x to the -2. So check your work. And now of course, we can factor the 14. So we have 14 x to the -2 times, now of course what's left is the x squared, and then of course we correct the -1 with a 14 downstairs like that. Now, if you will, we can just move the x squared downstairs without the negative. So we have 14 and factor the difference of two squares. So we have x minus 1 over the square root of 14 and x plus 1 over the square root of 14. And then, of course, in the denominator, we just have the x squared like that. So what's important about this problem is that this, again, goes back to what you did in your prerequisite courses. This would make an excellent example in the prerequisite where we would just solve this relative to 0. The thing about the critical numbers and the increasing, decreasing is that we invent the inequality, okay? We're not starting out with an inequality. Think about it. We're kind of changing the problem a little bit. Instead of the problem saying solve this inequality relative to some value, or maybe the zero's given, we've got to fashion that inequality. Okay, so that makes the problem a little bit more complicated, but not by much. So now when we analyze this, we do, if you notice here, have critical numbers, but we also have an infinite discontinuity that turns out to be a multiplicity 2, which is nice and simple. So now we can think of BVs, which include critical numbers. So we have 1 over the square root of 14, a positive number, and then we have the additive inverse of that. Now, one thing you might notice about this problem, and it's interesting, we've got a symmetric domain, but also the function is odd. That is, if you replace x with its additive inverse, that negative will factor and you get the negative of the original function. So we can just observe here, this is always good, you do in your prerequisite courses, that f is odd. And of course, the symmetric domain here gives us some indication to think about that. It's certainly only half of the definition. And then, of course, we have the 0 downstairs. So this is what I was talking about before. This is not included in the domain, so the 0 is not a critical number of f. These two are critical numbers, but this is just an infinite discontinuity, which we do need to consider when we're thinking about the sign of f prime. So don't forget things like that. By definition, it's not a critical number, but it is, as they say, critical in the analysis. So let's look at the number line. So we have, in this case, we'll just spread things out, -1 over the square root of 14. Then we have the 0, and then 1 over the square root of 14. So now what we can do, and this makes this fairly simple. Notice that denominator is always positive, and we're just going to touch there. But what we can do is do a very simple analysis. Let's just think of substituting for x a large value like 100, and then of course all of these factors will be positive. So we will be positive, but then of course, well, not much ink there. And then of course these exist multiplicity 1, so we'll have to cross here, right? But then we touch at the 0 because of multiplicity 2, so touch and then cross again. So that's not a surprise due to the fact that the function is odd. So now notice we have plus here, we have minus here, we have minus here, and we have plus here. So what we want to do is go ahead and fill in our little arrows. So we have increase, decrease. So we have a relative maximum. So we have f of -1 over root 14. And of course, now the 0 here doesn't make any sense as far as a max or a min because it's not in the domain. So we just disregard that, but it's actually important for the sign. And so here, notice we have the decrease, then we have the increase. So this is a relative min. So we have f of 1 over the square root of 14. Okay? So let's go ahead and summarize. We'll compute the values. Again, the sign analysis is the critical part of this. It will always be the critical part of the calculus, and we must abide by it. So first, let's just go ahead and get some of these values here. We can just compute 1 and then take the additive inverse. So we have f of 1 over the square root of 14. So this will be 14 times 1 over the square root of 14, really easy arithmetic, plus the reciprocal is just the square root of 14. So now notice the square root of 14 absorbs into the 14, so we get square root of 14 plus square root of 14, which equals 2 times the square root of 14. And this is the relative min from here. Relative min. Now, of course, since the function is odd, we don't have to compute this. This implies that f of the additive inverse of 1 over the square root of 14 will just be the additive inverse of this. So we don't have to compute that. You could, but you'll just get this. And this is the relative max. Again, the number line here tells us everything we need to know. This summary is exactly what you get from the increasing, decreasing. That theorem is critical for attaching the sign to the derivative. That is, we have the sign of the derivative that is attached to what? The slope of the secant line, which automatically gives us the comparison between the values of f. So again, so important. So now we can go ahead and do open intervals of increase. We'll just follow our sign convention. So we'll go up here, look for the positive. So we have negative infinity to -1 over the square root of 14. And then the other positive is down here, separate with a comma, 1 over square root of 14 to infinity. Again, just list them separated by commas. Now for decrease, we look for the negative sign of the first derivative, and we have, in this case, -1 over root 14 to 0, comma, 0 to 1 over the square root of 14. So what we want to notice here again is just some of the characteristics of this particular function. That is the existence of an infinite discontinuity, okay, at 0, which plays a role in determining the sign of the first derivative. So again, I can remember when I've taught courses in business calculus where students would often forget that because they were so focused on the critical number. So I had to remind them, just think of what you did in the prerequisite courses. If you're in the prerequisite course, you would never forget something like this because that would be one of the first indicators that you have a boundary value. That is a value, a real number for which the function is undefined. Okay, so of course, that's just presupposing that you have a division by zero that defines a vertical asymptote. Otherwise, it could be a hole in the function, which is a completely different situation. But in here, this is what I'm talking about. It's important to recognize the infinite discontinuities now that we actually have that vocabulary from the calculus. And then we can analyze the first derivative and then factor it so that we can find any critical numbers in conjunction with the infinite discontinuities, which we list here. We then plot, then we use the multiplicities to get a very simple sign convention. And then, of course, analyzing the pluses and the minuses, get the relative max and the relative min. So once we have that, the only additional computation is to actually compute the actual values. Now, if you happen to notice that the function is odd, or even if you notice that a function is even, that will certainly give you more efficiency in moving between values that are symmetric relative to the origin. But again, you think about even and odd functions, you've got to have that symmetry. With the odd function, you won't get the symmetry relative to the origin if you don't have something like this occurring. And with the even function is just the same. So that symmetric domain provides a certain geometry with the derivative that you can't escape. So again, why did you study the even and odd in the prerequisites? Well, of course, you studied trig, and that was important there. But now we're seeing how the even and odd is intimately connected with the derivative. So we're just, going back and forth. I mean, you're thinking, and again, I'm mentioning this, we start with an odd function, so the derivative is an even function, so this is not a surprise, okay? So there are certain checks that you will often have as you work through the calculus, which is just a repeat of all of the prerequisite information. So hopefully by this time you're realizing why you studied certain topics in the prerequisite courses, because now we have to rely upon them to do the calculus. So I hope that you now see the importance of the mean value theorem, Rawls' theorem. You see the importance of Fermat and EVT, but until we were able to find a connection to some object that told us, what's this function doing? When does it increase? When does it decrease? Do I just compute a bunch of values? That is not precise. The calculus gives us the precision in the arithmetic that we need to solve these problems. And as we continue in the sections in this particular chapter, we will see how the derivative continues to give us valuable information, so that we can actually solve some really, really interesting problems. Okay, well, that's all I have to say about this. Enjoy the work on these theorems, and we'll see you soon.